So we have seen how waves turn into unstable waves, and how overturning of waves occur in some given conditions, right? Which particularly involves shear flow, and in particularly when the velocity difference between two layers are very large, we get overturning, and that brings instability into the system, right? So that we have seen physically, we saw several cases or images, but now let's try to analyze this particular case or problem mathematically. Okay, so we will start with the simplest case of two parallel fluid layers, okay, that meet at zero thickness interface. So what does it mean by zero thickness interface? So here we are assuming there are these two fluid. This is layer 1 and this is layer 2. Okay, where layer 1 has the density of rho 1 and layer 2 has the density of rho 2, which is greater than rho 1. Okay, so initially these two fluids are stable, and they are stratified and stable, but we also assume that there are two different velocities. So upper layer is moving with velocity u1 and lower layer is moving with velocity u2, where u1 is not same as u2, and in this case we are assuming u1 is greater than u2, and that means there is a shear flow. See, this actually means that shear flow condition, which basically tells you when there is velocity difference in the transverse direction, right? So this is our basic condition, and we also assume that these two layers are, both the layers are infinitely deep. Okay, so both at the upper layer goes infinitely upward and lower layer goes infinitely downward. So we are not worried about its maximum thickness, so we assume that the effects of wave that we experience here is not affected by surface conditions. Okay, and obviously we are assuming both the fluids have different densities. So once we have defined this condition for two different fluids of different velocities and different densities, we can actually start by defining or writing Navier-Stokes equation for both the fluid layers separately. Okay, and once we have written the Navier-Stokes equation, we can simplify it by assuming linearization, as we already did that for case of a wave, right, surface wave. So you understand what linearization is, and then we tried to apply some perturbation to the basic flow, right? So basic flow is when we have this velocity u1 and u2, but then there are some perturbation that basically means that there is small changes in velocity depending on the wave, and that change in velocity is with respect to the wave condition, and now with increasing wave amplitude with time, that the velocity will also probably change, the perturbed velocity will also change, right? And once we have done this, we will do normal mode analysis, which basically makes the problem to be an eigenvalue problem, and we solve that problem. Okay, so this is like complete let's say the methodology for finding instability analysis or stability analysis, but we are not going to do this for this course because the derivation becomes very complicated and very lengthy, and that is why I have just listed down the steps, but I am finally going to write the stability condition only, rather than giving you or going through complete derivation. Okay, so we get the stability condition in form of wave frequency or phase speed, and these are again two different things that we have studied in the last lecture, where phase speed is something we defined as c, and wave frequency is defined as omega, right? And there is a relation between omega and c, that c is omega over k. Okay, if you recall that, you should be able to, so if you are able to go back to previous lecture, you should be able to figure out what is the phase speed of a wave and what is the wave frequency, and both of them are related to each other, where k here is the wave number, where k is actually related to 2 pi by lambda, and lambda here is the wavelength, right? So these all things we have studied. So now the condition we get for overturning wave is this is in form of the phase speed c, and that is given as rho 2 u2 plus rho 1 u1 over rho 2 plus rho 1 plus minus rho 2 minus rho 1 over rho 2 plus rho 1 g over k minus rho 2 rho 1 over rho 2 plus rho 1 square u2 minus u1 square, and the complete bracket is inside the square root. Okay, so this is the condition we get for the phase speed in case of a unstable wave, where once again c is the phase speed, right? And this equation that you get here can also be called the dispersion relation, which we already derived for a stable wave, right? And what you see here is that c has both real as well as imaginary part. Okay, likewise, and this is actually coming from omega, which I think we are using the other type of omega, is omega r plus I omega I. Okay, so omega has both the real and imaginary part. Likewise, the phase speed has both the real and imaginary part. So this obviously, as we discussed, that this solution is derived based on the normal mode analysis, and that is why we have these conditions. And what actually it means is, if c is or if c is only real, if ci is 0 and c is only real, then the system is stable. And if ci is non-zero, okay, which means that c has the imaginary component as well, then the system, or by system we mean the wave, is unstable. Okay, in that case, basically the amplitude of the system grows and grows further, and that overturns the wave. Okay, and if you look at this solution, what exactly you see here is there are different terms. Let's call it A, this is B, and this one is C. I think I should not use C because we have already been using C here. Let's call this as D. Okay, so for Ci to be not equal to 0, the value of D must be greater than value of B, right? Because you see this is within the square root and it is only possible when D is greater than B, right? D is greater than B. That actually means that your rho 2 minus rho 1 over rho 2 plus rho 1 G over K is smaller than rho 2 rho 1 over rho 2 plus rho 1 square u2 minus u1 square. Okay, so I think I should write it B is smaller than D. All right, so when B here, the term B is smaller than term D, in that case you get an imaginary value for the phase speed, that is C, right? Phase speed is C, and indirectly that also gives you the imaginary value for the omega, that is the frequency, because here the K is wave number and that is always positive. Okay, K is always positive. All right, so this is the criteria we get for the system to be unstable. Okay, and if we have to analyze it little further, this will give you rho 2 square minus rho 1 square G over K is smaller than rho 2 rho 1 u2 minus u1 square. Okay, so now from here we can actually try to find a critical wavelength for which, below which the system is always unstable and beyond which the system is always stable. Okay, so if you recall, K is defined as lambda 2 pi over lambda. So this particular condition will give you rho 2 square minus rho 1 square lambda G over 2 pi is smaller than rho 2 rho 1 u2 minus u1 square. So that basically means that lambda should be smaller than 2 pi over G rho 1 rho 2 over rho 2 square minus rho 1 square u2 minus u1 square. Okay, or here we can also define lambda critical as 2 pi over G rho 1 rho 2 over rho 2 square minus rho 1 square u2 minus u1 square. Okay, so this is the critical wavelength of the wave below which the wave is always unstable and beyond which wave is always stable. Okay, so if lambda is smaller than lambda critical, the wave is unstable and overturning will occur. If lambda is greater than lambda critical, then wave is stable, right? So you can see that lambda critical depends on u2 minus u1 and rho 2 minus rho 1. So what it actually means is lambda critical increases with u2 minus u1. Okay, and other point is lambda critical decreases with rho 2 minus rho 1. Okay, so what actually it means is larger the velocity difference between these two layers, right? We are talking about, let's say this is u1, right, which has density rho 1, and then we have u2 and density rho 2. So if u2 is, the difference between u2 and u1 is very large, that will increase your lambda critical. So basically in most of the cases you will have unstable wave, because lambda critical is the critical value for going from unstable to stable wave. So delta u, increase in delta u increases the value of lambda critical, right? That means there will be more and more chance of wave to be overturning. But if you increase delta rho, lambda critical decreases. That means for majority of cases your wave will be stable, and only when the wavelength is extremely small, then only it will be unstable. So this depends both on delta u and delta rho, and we will analyze these particular cases in more detail in these limiting cases now. So let's first consider case 1, where we will assume that u1 is equal to u2. Okay, so that actually means that there is no shear flow. Both the velocities are same, and wave is still there, and there is density difference. So rho 2 is still greater than rho 1, but u1 is equal to u2. In this case, what do we get from the dispersion relation? Let me copy that from here. Okay, so if u1 is equal to u2, what do we get is c to be equal to u plus minus rho 2 minus rho 1 over rho 2 plus rho 1 g over k, right? Because this term basically becomes 0, right? And then this actually means that this term is always positive. This is positive, that means C is always CR, and CI is equal to 0. Okay, and if CI is equal to 0, that means the system is, implies that system is always stable. Okay, so when both the velocities are same, and if there is a wave, but that's happening because of density difference and not because of shear flow, so the system, whatever wave that is forming, will always be stable. It cannot be unstable because Ci is equal to 0. Okay, the imaginary part is equal to 0. Okay, which actually also means that, which implies that the instability occurs only due to a shear flow if the system is stable stratified. Okay, that what actually it means is this particular thing means that your rho 2 is greater than rho 1. That means your heavier fluid is under the lighter fluid, right? So that is in equilibrium, and in this case the system will always be stable if there is no shear flow, or in other words, only shear flow can bring instability to the system. Okay. And now if you analyze this further, for the so if we use this criteria and go back to this equation that we have derived, this and I just found out there is a mistake here. So this should be, there should be a minus sign here, right? So now, assuming that there is either u1 is equal to u2, and now considering this equation, if we assume u is equal to 0, or in other words, u1 equal to u2 equal to 0, the equation we get is this, where this becomes 0, right? And for the case that we have considered before, if rho 1 is much smaller than rho 2, as we did for the wave in previous case, when we have water and this is air and there is wave, that is the wave, that the surface wave that we analyzed before, what we get here is C is equal to uh, 1 minus rho 1 by rho 2 over 1 plus rho 1 by rho 2 g over k 1 by 2. So this basically gives you C equal to g over k, or the square root of g over k, right? Because rho 1 by rho 2 is much smaller than 1, right? This is a case we have considered. And now if you go back and look at your analysis, you will find that this is the equation we already got for right. This is the dispersion equation we got for deep water waves, where your phase speed is inversely proportional to the wave number, right? And this is the exact relation we get, and this is applicable uh, when your kh is much greater than 1, right? And also your u1 is equal to u2 is equal to 0, and rho 1 is much smaller than rho 2. So this is the case that we have is considered for the surface water waves or surface gravity waves, and we get the same equation from this limiting condition case 1. Okay, now let's consider another limiting case, and we will call it case 2. Case 2, where we assume rho 1 is equal to rho 2, but u1 is not equal to u2. Okay, so now if we use the same equation that we have got here, we'll copy from here. Okay, this will give us C to be equal to, so rho 1 is same as rho 2, and u1, so this will become u1 plus u2 by 2 plus minus, the first term will become 0, so this becomes minus u2 minus u1 square or 2. So basically that becomes equal to u1 plus u2 over 2 plus minus imaginary of u2 minus u1, right? So now you see there is always an imaginary component in this case. So basically CR is not 0 when rho 1 is equal to rho 2, but u1 is not equal to u2. So that actually means is whenever there is shear flow, stratification does not matter. If there is shear flow, there is always a chance of instability in the system. So there will always be some wave speed, some wavelength for which the system will be unstable. However small the delta u is, the system will be still unstable because this value, as you can see, is always positive. So the CR is always greater than 0 if there is even a small delta u in the system, right? So this again means that complete instability is driven by the shear flow, not necessarily by the density difference. In fact, the density difference works in favor of stratification. So that is a factor that tries to keep the system stable, whereas delta u tries to make the system unstable, right? So basically what it means is delta rho keeps the system stable, whereas delta u makes the system unstable. Okay, and this is something we already saw in case of previously when we were talking about the basics of the wave, right? Where delta rho works as stabilizing agent, whereas delta u works as destabilizing agent. Okay, and that is why this lambda critical also that we tried to find out has a smaller value if delta rho is, so it has larger value if delta rho is large. That means most of the flow will be unstable, and is just the reverse in case of delta rho.